Okay. So during the first week, we covered, basics of machine. Actually, I started with software environments, I think, and then afterwards we went over some overview of machine learning. And I think the very first class we just went over the syllabus, and then software environments, and then the third class last week there was only one regular lecture, so that was about the overview of machine learning. So, and then Mihir conducted a session of all the programming issues and so on. And today, I think Mihir has a quiz ready at the end of the class, right, Mihir?
Yes, Professor.
Yeah. Okay. So we're gonna have 15 minutes for the quiz at the end of today's class. Material is what we covered last week or last 2 weeks, I suppose. And so that's the quiz. There's no breakout room today. We do that on Wednesdays. And okay, so today's topic is linear algebra for machine learning. Sounds like a very, very basic topic, but it turns out it's a worthwhile topic to begin in machine learning. So my lecture for today is titled Linear Algebra for Machine Learning. It's not simply linear algebra. So what is the linear algebra that you need for machine learning? And it's worthwhile to review it. We're going to follow this up with some probability theory for machine learning next time. But there's quite a bit in linear algebra for machine learning. Let's see how we do today. I don't think I'll be able to finish all of it, but it's extremely interesting stuff. Although you might say, look, I did linear algebra, and what more do I need to know? Turns out it's many machine learning solutions can be just done using linear algebra. And I saw a cartoon once. It said, what is machine learning? And you got all this pile of data. Somebody has a pile on the ground, pile of data, and it is explaining machine learning is simply applying all kinds of linear algebra to that to get a solution, right? And if it doesn't work well enough, add some more data, that kind of a thing. So a linear algebra solution may be enough for some simple machine learning problems. About what kind of linear algebra we're talking about? Linear algebra where we multiply vectors with matrices. Mostly our inputs are all vectors. They're all vectors of data, and we multiply them by matrices and transform them. When we multiply them by matrices, we call it as linear transformations, and we get other vectors. And so we need to know about this kind of algebra, which is linear algebra, and within which we'll very quickly see some simple machine learning solutions to some machine learning problems, such as for regression. Linear regression can be solved using simple linear algebra. There's nothing more than arranging everything in the form of what's called a design matrix, where the rows and columns correspond to the samples and the feature components, right? And so just that much that can be enough for certain solutions. And there are some famous machine learning methods which completely arise from only linear algebra. So you can have a solution for the regression problem using linear algebra. Don't we need anything more than that? Then why do we study machine learning? Well, it turns out some of the linear algebra solutions are not that practical when things get big, in terms of number of elements and number of data points and so on. You need iterative solutions and so on. So that's when we get into gradient descent and things like that. And other than a linear regression problem, we also encounter some ideas called eigenvalue decomposition of a matrix, or we encounter what are called singular value decomposition of a matrix, SVD. and they look a little complicated, but they are extremely powerful, completely arising from linear algebra. There is something called singular value decomposition, and that is turns out to be useful for solving problems such as recommendation systems, right? So an important application of machine learning is to recommendation systems. Uh, such as, when you go to Facebook, they're recommending to you to read something. They're just sending you stuff. And how do they figure that out? Or, of course, Amazon, right? When you're ordering some item on Amazon, it says, oh, people who bought this also bought this. They're recommending it. It's a recommendation system. It's an extremely useful thing for social networks such as Facebook, but also for these online vendors like Amazon and so on, or maybe Netflix, right? No, I'm not much of a user of Netflix yet. I'm just getting more used to it. But I think they do that, right? If you had liked these movies, they're going to recommend to you. You might like this movie as well. It's a recommendation system. And I'm not much of a user of TikTok. I assume some of you are users of TikTok, right? You're familiar with TikTok? Just nod. Okay, you are. I was in India. I spent 6 months in India. I just came back 2 months ago. Yeah, even some of the, we had a person who helped around the house, and her daughter who was just finishing high school, and she was very familiar with TikTok in India. Even people who are not, you know, in the higher strata of society or and so on, very familiar. The kids, particularly, they're familiar with TikTok, and very popular in India, TikTok. And I was just reading in the newspaper the other day that said the most important technology in TikTok that they're all tussling about, right? U.S. and China are tussling about who's going to own TikTok. And it seems the most important technology in TikTok is its recommendation system. That is the technology that is valuable. Apparently, they have very good recommendation systems that presents to you. If you watch this dance video, you will like this other dance, that kind of thing. I don't know, right? That kind of stuff. Is it all just based on linear algebra? And no, there are really more sophisticated methods other than linear algebra, which is content-based and so on. They call it as that. But today we'll actually look at linear algebra, and we come across how recommendation system can be implemented using linear algebra. So anyway, I'm trying to get you excited and interested, and don't think that linear algebra is a boring topic. So it is actually sounds like a very basic mathematics topic, but the way you look at it is what's going to make the difference. That it is a powerful. So we're going to look at linear algebra, which can provide you with solutions for a linear regression, predicting a value, or a recommendation system. And it can also be used to implement an algorithm called principal components analysis, which is to take a high dimensional data and reduce it to some lower number of dimensions, because the number of dimensions can be very high, impractically high. And like if you have thousands or even millions of elements in your vector, which can arise out of let's say, even a still picture on your camera can be a million pixels long, which is very big. You can't even multiply that. So what if you reduce it to a certain manageable number, maybe 1,000 or 500 or something like that? How would you do that? And you can use something called principal components analysis, which is also completely derived from linear algebra. Just take your data, arrange it as a matrix, and start multiplying it. That, and all you need to do is, all the algorithms you need are simply based on matrix multiplication and inverting a matrix and operations like that. So we got to know what is matrix multiplication, what is inverting a matrix, what is transposing a vector. Uh, Ideas like that are all in linear algebra. Okay, that's my very long motivational introduction to linear algebra. Okay, so I'm going to share my screen to my slides on linear algebra. Okay, so I presume you can now see the slides, linear algebra for machine learning. I can make this larger and okay, I think that seems to be working, linear algebra for machine learning. All right, so this is the topic. This is quite a long set, set of slides. It's turned out to be one of my more popular slides because it's on my website for this course. Introduction to machine learning. So anybody in the world can look at these, and I get more references to this than some of the other standard topics in machine learning. Sometimes in an introductory machine learning course, they skip this topic saying, okay, linear algebra, you must know, right? But it turns out linear algebra for machine learning, as I said, it's a very worthwhile topic to look at because you encounter some machine learning topics already and see the solutions for it using linear algebra. And if you can solve a problem using simple approaches, you must do that rather than simply saying, no, I'm going to use this, use an iterative method using gradient descent and so on. So this one doesn't involve anything of the order of gradient descent here. It's just matrices. Okay, so let's begin. Let's see however much slides I can cover in the amount of time I have. Mihir is going to interrupt me saying that's all the time I've got. Okay, so what is linear algebra? So linear algebra is the branch of mathematics concerning linear equations. Okay, so we talk about linear equations such as a1x1 plus a2x2, etc. plus an(xn) equal to b. So these are linear, and like we are given an input vector x equal to x1. You look at it on the right hand side here. We have x equal to x1 through xn. We call this a vector, and we show this x by a bold x, indicating that's a vector, and we indicate all the elements as italics, and they're not bolded, indicating they're all scalar values. The subscripts say there are n elements here. Usually we think of our vectors in machine learning as column vectors like this. And we can transpose the matrix by converting it to xt, means x transpose. That gives us a row vector where x1, x2 are arranged in a row rather than in a column, right? So we have x, we assume x is some input. This could be like an image captured by your camera is x, which are all these pixel values here. And so this is saying we'll multiply every one of these by a scalar value, which is what's going on here, a1, x1. And since they're all scalar values, we're multiplying them by these weights, let's say weights a1 through an. You can all add up all these numbers together. It gives a number b. And so we are saying this is linear. We are not taking like the square of these x's. That would make it quadratic. Quadratic in x, or it's not quadratic in the elements. They're all linear. So this is called a linear equation. It's not ax squared plus bx cubed. It's not a cubic or a quadratic. It's linear. So this is the kind of algebra we're talking about. This is where the word linear comes in. So it's a linear equation. In vector notation, we say A transpose x equal to B. You see, we're multiplying this A vector, all these A's put together. They're also a vector, there are n of them. And we make it into a row vector. It's also defined as a column vector. Everything is defined first as a column vector. When we do a transpose, it becomes a row vector. So it is, it's a 1 by n matrix you can think of, one row and n columns. So it's 1 by n. And this one, x is n by 1, n rows, 1 column. So you can multiply a 1 by n with a n by 1, give us a 1 by 1, which is a scalar value here, right? So we say it's a linear transformation of X. So we are transforming this with these multiplications, and we get this scalar value over here, right? It's a linear transformation of X. So linear algebra is fundamental to geometry for defining objects such as lines, planes, rotations. So if you want to define these things in a 3-dimensional, this is only 3 dimensions is being shown over here. We can be dealing with an n-dimensional space because we have n of them. And in 3 dimensions, we would be defining a plane, and that plane is defined by means of an equation in 3 dimensions. And then there are lines. Of course, we'll be, when we go to a multidimensional space, we call it as a, we don't call it a plane anymore. We call it as a hyperplane, right? Hyperplane. And but mathematically, the concept is the same. And so this is very central to the geometry of these spaces. So linear algebra is about this kind of stuff. Why do we need to know it? All right, why do we need to know linear algebra? Well, linear algebra is used throughout engineering, right? Okay, so engineers will readily say, look, I've used linear algebra all over. But we are largely computer science people here. And linear algebra is based on continuous rather than discrete math. We're talking about continuous spaces here. We talk about Rn, that is the continuous space of n dimensions, real numbers. And computer scientists have little experience in it. So one more reason why we need to restudy linear algebra. As a computer scientist, you might not have done much with linear algebra before and may not have felt it being useful when you were encountering it in a required course or something, right? So, but linear algebra is essential for understanding machine learning algorithms. Constantly we talk about vectors and matrices and transposes and so on. So better have this as in your toolbox. We convert input vectors x1 through xn into outputs by a series of linear transformations. That's what machine learning algorithms do. They take a input and we transform it to values, and we end up series of them. In deep learning, we have layers and layers of these transformations that take place. So what do we discuss in this long set of slides? Is we discuss concepts needed for machine learning, but we omit other aspects of linear algebra. There might be so many things about linear algebra that one needs to know about analytical geometry and so on. So we'll focus on what is needed for being a machine learning expert. So what are all the topics here? See, I'm just putting it up because I won't be able to go over every one of these at this pace because it'll become a course on linear algebra. All right, so we'll cover a few of these topics, although I find all of them are very interesting. So the first thing we look at is scalars, vectors, matrices, and tensors. Scalars are single elements. Vectors are like a column vector or a row vector we just saw. Matrices are 2-dimensional arrays. Tensors are groups of arrays. Like we have an image in red, green, and blue. There are 3 layers of matrices corresponding to the 3 colors, and we call that as a tensor. And a video would be a color video would be these things repeated over time. That would be a 4-dimensional or 5-dimensional tensor and so on. So quite often these machine learning algorithms deal with these kinds of tensors. So we need to know about multiplying matrices and vectors. We just mentioned that. And we need to know what is meant by an identity matrix, which has got all the diagonal elements are all 1, rest are 0. And an important concept is the inverse of a matrix. If I give you a matrix, a 2-dimensional array, what do we mean by its inverse? When you multiply a matrix by its inverse, you get an identity matrix. So it's like a reciprocal. Inverse is a generalization of the idea of a reciprocal in ordinary arithmetic. If I say 5 and I ask you what is the reciprocal of 5, it says 1/5. If I multiply 5 by 1 over 5, the answer is 1. It's like you're getting an identity. So that's the same idea generalized to matrices. And then there is the concept of linear dependence and span of a matrix. That's a kind of specialized thing. We probably don't need that much. We don't see that span too much. But anyway, those are all in part of this lecture. Norm is an important concept. It's about the length of a vector. If you think of a vector, we just saw how a vector is written x1 through xn. In n-dimensional space, that vector will be a point in that space. Because if we specify the values of x1, x2 through xn, that we are specifying a point along each dimension, and together they define a point in this multidimensional space. So isn't that interesting that if you have an image as your input vector, like the image captured by your camera, then we're saying, well, how many pixels are there? If you say it's got 1,000,000 pixels, then we say, well, it's just a point in a million dimensional space. All that data is just a single point in a million dimensional space, which means every possible picture in your camera or taken with your camera is a different point in that very high dimensional space. And sometimes we would like to know what is the length of that vector. That is from the origin, how far did you have to go to get to that point? And that length is measured by norm. Call it as a norm. We talk about a Euclidean norm or an L2 norm, where you're squaring the values along each dimension, adding them all up, taking the square root of that. It's how we measure the distance between 2 points in an ordinary two-dimensional plane, right? So that's norm. And then there are all kinds of special kinds of matrices and vectors that we encounter. Diagonal matrix is one where we have only elements along the diagonal of the matrix and the rest are all zero. It's called a diagonal matrix. And then there are things like symmetric matrices. The elements on the right side of the diagonal are all the same as the elements on the left side of the diagonal. We call it the symmetric matrix. And symmetric matrices occur quite often in machine learning. Yeah, particularly if we are dealing with covariance matrices. A lot of machine learning is about statistics. So we have different variables, and we're talking about how correlated these variables are. And the correlations are all put together in a matrix called as a covariance matrix. All right, variances, I should say. Correlation and covariance are related, not exactly the same thing. So the variances are all put together, and that usually is a symmetric matrix. The covariance between A and B is the same as between B and A, so those elements become the same. And then we have special kinds of vectors called eigenvectors, so on. And then we can decompose a matrix using eigen decomposition. That turns out to be a concept you occasionally encounter. If you're trying to read something about an algorithm in machine learning, suddenly you'll come across, we need the eigenvectors and so on. So this is where you come to find out, okay, what is that? I've forgotten, eigenvalue, eigenvector. And then there is this thing I already mentioned, singular value decomposition, which is used in recommendation systems for one. It is also used in what is called as the Moore-Penrose pseudo-inverse. Turns out the inverse is an important concept, even to define a normal distribution. The simplest distribution in continuous space is a Gaussian or a bell-shaped curve. The bell-shaped curve is, we normally know it in one dimension, about one variable. But when you're talking about a bell-shaped curve in multiple dimensions, to define it, you need the variance along each direction, and you need the covariance along each direction. And so you're going to end up with a covariance matrix here to define the normal distribution. And sometimes the covariance matrix we say is a singular. In the sense, if you take its determinant, it turns out to be 0. So what do? We'll have to divide that by that quantity, and you can't divide by 0. So we need an approximation to it, and that's called a Moore-Penrose pseudo-inverse, not the real inverse, some approximation to it. And how do you define it? Well, you need the idea of singular value decomposition to define that. And then comes the idea of the trace operator, which is summing all the diagonal elements. That's a simple concept. And the idea of the determinant of a matrix, that is it's a value, a number that somehow characterizes the matrix. And the last one is the principal components analysis, which is about reducing the size of the input space. All right. Okay, so we'll do as much as we can. So we'll begin with scalar. A scalar is a single number. In contrast to other objects in linear algebra, which are usually arrays of numbers. It's not like a string of numbers, just one number. If I say 7, it's a scalar, or 253 is a scalar, or 3.141517 or whatever, right? That's pi, the scalar value. And we represent them in lowercase italic x, right? Scalar. These scalars can be real valued, or they can be integers. So we can say let x belong to R when we say it's a real valued number, be the slope of the line. Slope becomes an important concept because we are usually interested in taking the derivatives. You already encountered that when we saw the logistic regression code, computing the derivative and so on. It's a value, it's a real valued scalar. And we also sometimes need, discrete numbers, like let n belonging to a set of natural numbers be the number of units. We talk about number of units in a neural network is how many sigmoid elements are there in the network. So we say that's a natural number scalar value. It's not a vector, it's a scalar. A vector is an array of numbers arranged in order, each number identified by an index, written in lowercase bold such as x. So we just saw this already. Its elements are in italics, lowercase subscripted. If each element is in R, it's a set of reals, then we say x, the italic x, which is a vector, is in Rn, we say. It means it's the n-dimensional real space. We can think of vectors as points in space. So if I give you the values to each of these, the real values, 7, 14.5, and whatnot, defines a point. And each element gives a coordinate along an axis. So a matrix is a 2D array of numbers. So each element identified by 2 indices. So this is all the kind of notation that's common in machine learning literature, denoted by bold typeface A. Elements indicated by name in italic but not bold. A11 is the top left entry. So here is a matrix. It's got 4 elements. A11 is the top left entry, and AMN, an M by N matrix, it is the bottom right entry. There's some notation they're giving here. It may not be very common. We can identify numbers in vertical column J by writing colon for the horizontal coordinate. And we can talk about AI colon is the ith row of I colon. So these are all i's you're going through ith row. So we're selecting the ith row, and then we run through all the elements here. We can denote it like that. And A colon J is the jth column of A. So there's some notation, which is not that important, but it's kind of interesting. How do you specify this row or a column of a matrix? And we say A has shape of height M and width N with real values. So we talk about a shape of a matrix. The shape, how many rows and how many columns is the shape of the matrix. Height M and width N, right? With real values. Then A belongs to Rm cross N, which means the matrix is in this set of reals M by N, all right? So that's kind of notation here. So after we define scalars and vectors and matrices, we define a tensor. And sometimes we need an array with more than 2 axes. And an RGB color image has 3 axes. And a tensor is an array of numbers arranged on a regular grid with variable number of axes. See figure next. And we denote a tensor with this bold typeface A. And elements ijk of tensor denoted as aijk. And here are some shapes of tensors. So this is just a vector, one-dimensional tensor, is a two-dimensional tensor, is a three-dimensional tensor. This could be like, this is a picture, two-dimensional picture, grayscale picture, and we would have 3 grayscale pictures with 3 layers here. We'd call that as the color image, and that would be a 3D tensor. 4D tensor would be the color image over a period of time. So you would have 3D tensors at different points of time. There would be a 4D tensor, a video. Maybe this is a collection of videos is a 5D tensor. All right. Maybe collections of collections is a 6D tensor. I don't know. So this is generalizing these concepts. Actually, we encounter 4D, 5D tensors quite often in deep learning, where we go about obtaining, applying to the same image different filters. And say this is an image, and then we apply some filters to each of these, and these are all with filtered columns through different eyes, so on. So there can be very quickly 5D tensors and so on in machine learning and deep learning. Okay, and then there are some basic simple manipulations which you should get familiarized with in looking at anything in machine learning. Transpose of a matrix, an important operation on matrices. The transpose of a matrix denoted as AT. AT is A transpose. So this is just changing the rows into columns. ATIJ is equal to AJI. So you can think of transpose as a mirror image. So let's see, A equal to A11, A12, A13 here. So when you transpose it, it becomes A11, A12, A13 like this, right? So this row has become a column, this row has become the second column, this row has become the third column. I suppose you can also say the column here has become the row, that way also you can say. And it's also a mirror image across the diagonal line. You can think of it like that. So called the main diagonal running to the right, starting from the upper left corner. So we're kind of putting this is the mirror, and we're putting A21 over here, right? A31 across the mirror here, and so on. So there's different ways to look at it. The idea of so there is a transpose of a vector, the transpose of a matrix. This is transpose of a matrix here, A transpose. And you see, to give the normal distribution, we need a covariance matrix, and we're going to also show it as its transpose, and we're going to compute its inverse. All of that is needed for a very simple specification. So you can think of vectors as special case of matrix. Vectors are matrices with a single column, often written in line using transpose. We write this is a vector written like this. We don't, it's cumbersome to write a column vector in text. You would simply show it as x equal to x1 through xn transpose. You write it like that because you can write it in a row. If you're writing a paper, you can just type it like that without having to have a picture of a column vector. And a scalar is a matrix with one element. So it's just saying that vectors and scalars are special cases of a matrix. So matrix addition is a simple operation. We can add matrices to each other if they have the same shape. That's important. They have to have the same shape. You can't simply arbitrarily add matrices. So they got to be both m by n, for instance. If A and B have the same shape, height m, width n, I can get from A plus B equal to C with such that element Cij are Aij plus Bij. A scalar can be added to a matrix or multiplied by a scalar. So, and here we are adding a scalar can be added to a matrix or multiply. We are multiplying B by A. And what this means is Dij is equal to A times Bij, that element, plus C, right? So it can be, I guess this is getting a little specialized notation here. Sometimes what happens in machine learning and deep learning is we need some specialized notation which has not been defined by the people in mathematics who teach linear algebra. They hadn't thought of some notation that would be useful because these algorithms are all largely doing matrices and stuff like that, and we need certain things that are needed. So there are some new notation comes in when we talk about linear algebra for machine learning. Vector added to a matrix, you can add, and we use called broadcasting, since a vector B is added to each row of waves. So there is all some of these operations. Anyway, not that you have to remember every one of these things. At least you know where to look when you encounter this kind of notation suddenly coming up in code or in algorithms and so on. So this is the kind of thing. Multiplying a matrix is an important concept. A product C equal to AB to be defined, A has to have the same number of columns as the number of rows of B. So they have to be, I don't know what do you call it, compatible. So if A is of shape M by N, B is of shape N by P, then the matrix product C is of shape M by P. So M times N times P is equal to M times P. Right? So you can multiply two matrices. This is exactly what goes on in neural networks. You present a matrix as input. This matrix is the image or whatever vector you have. And we say, oh, we got a bunch of weights waiting for you. And we say, take the product of the two and create a new one. So, and when we're doing that, so A is multiplied by B and we create something C, which has a different dimension. We started out with an image, let's say M by N. This was it was a 1,000 by 1,000 image, and we multiplied it by something which may be 1,000 by 100. So suddenly we reduce the dimensionality of this by doing this multiplication because we get a smaller. So a large thing has become a smaller thing now. This is the kind of stuff that goes on in deep learning and in convolutional neural networks and so on. Mostly this kind of multiplication. Note that the standard product of two matrices is not just the product of two individual elements. Yeah. When we are multiplying two matrices, we aren't simply saying correspondingly we are multiplying every element. It involves an addition over the rows and columns and things like that, like this. But if you want to take a matrix and multiply it by another matrix, element by element, you want to take the product. That is not a very common operation. It is not even defined by the mathematics folks. But machine learning people said, oh, we do need that. We are going to be sometimes multiplying all these elements and scale it or something. Such a product does exist and is called the element-wise product or the Hadamard product. It's written like this. The symbol is called coin. A coin B means A and B are compatible matrices, M by N, and you can multiply the corresponding elements. That is this operation.
Just a quick question. How is that different than the standard product? Again, like the C equals AB, how is that different with the coin?
Oh, the coin is element by element. It's like addition, no? Just corresponding elements are being, that is coin, that is Hadamard. This one is, when we say we multiply, A and B, A is M by N, B is N by P, the elements of this are, running over K, A, I, K, B, K, J, run over all these elements, take the product of all these elements, add them all up together. So it's like you're taking a column here, I mean, a row from one, a column from the other, and we are correspondingly multiplying all of them, adding them all up. That becomes one element. This is much more involved. All right. So you see, we are running through the if it's a row and column, we're running through the columns of A and we're running through the rows of B, and we are multiplying them. And it's possible because we are we made sure it's one is M by N, other one N by P. So it's a much more complicated operation to obtain a product here. Okay.
Okay.
Right? Yeah. Just construct a small, matrix and show yourself what does that involve. Make a 1 by 2 and a 2 by 1, right? Or something like that. Put some numbers in it and multiply it. How would you do that? So you need to kind of multiply corresponding elements and add them up. Okay, that's what's going on. A good question. Multiplying a matrix is multiplying two matrices is more complicated than element, whereas adding two matrices was simple, element by element addition. This one is more complicated, multiplying matrices. Multiplying vectors, dot product between two vectors x and y of the same dimensionality is the matrix product x transpose y. There are two ways of multiplying two vectors. One is the dot product, which gives you a scalar value, right? So you take a n by 1 by n times a n by 1. If you do that, you get a scalar value. You can think of a matrix product C equal to AB as computing Cij, the dot product of row I of A and column J of B. So you can, but there's another way of multiplying two vectors, which gives you n by 1 times n, 1 by n gives you an n by n. So that would be, so you can multiply two vectors and either get a scalar or you can get a matrix. Either we are reducing the dimensionality or we can increasing the dimensionality. Dot product gives you a scalar value. So matrix product properties is just an observation here. Distribute over A times B plus C. This is kind of specialized. A is equal to AB plus AC. Associativity. Not AB equal to BA is not always true. When you multiply two matrices, depends on the order in which you multiply. Dot product between two vectors is commutative. X transpose Y equal to Y transpose X. Transpose of a matrix product is a simple form, all right? So some interesting identities, okay? So we've got all kinds of operations now. So now we can have all kinds of interesting theorems out of it. Here's an example of a flow of tensors in machine learning. We got a picture of Buddy here. Where's Joyce? Look at this, my example here. We got a cat here. All right, this is not a tabby cat, but it's a black and white cat here. And so this machine learning program is to say, is this a cat or is this a dog or is this a ship? Look at the classes here. It comes from some data set which somebody created with some small number of classes that pictures of cats and dogs, which are easily available on the internet. I suppose everybody loves looking at cats and dogs. I guess they also like looking at ships, and they had all these images available. And the machine learning program is to say what kind of a picture is this. So we can think of it as a vector x is converted into vector y by multiplying x by matrix W. So what goes on in the machine learning program, this input image, this cat, is stretched into pixels in a single column. Let's say there are only 4 pixels. We divide it into a 2 by 2, which gives you 4 values. And the values are 56, 231, 24, and 2. These are the elements x sub I. Of course, if it's going to be a high resolution image, that's going to be million long. We only have 4 here. So a machine learning program, a linear classifier, such as y equal to wx transpose plus b, that's all it does. We say a linear classifier has this form. The input x, which is this, is multiplied, and we're making sure that they're compatible by transposing it, right? this is a column vector. We're going to have to transpose it. And then we multiply it by a matrix W. This is a matrix W, which has got all these strange numbers, 0.2, minus 0.5, 0.1, 2.0, 0, etc. Cleverly constructed matrix here, W. And we take this W and we multiply it like this, WX transpose. And to that we add B, which is in this case a vector with these values here. And when you do that, we get values. We get, it becomes a vector. So multiplying this, this matrix by this vector gives you a vector. To that vector, we add another vector. We get minus 96.8 for a cat and 437 for a dog and 61.95 for a sheep. And presumably, the lower the value, the better it is. And maybe it's computing something like a loss or something like that, which is very small here. And we say, okay, it recognizes it as a cat and not a dog, which has got a different kind of value, and not a sheep, which is in between, but it's not a negative value. So the whole machine learning problem then becomes, how do you figure out this W? Of course, this is all fixed. You're going to get this from whatever camera, whatever animals or objects you're taking pictures of. So you're going to get X from. W is the clever part, B is the clever part. So a machine learning program would learn W and B. And so that's where the algorithms come in for a classifier. Sometimes we have a linear classifier. We call this B for bias. W for weights, B for bias. F is a function that is mapping the xi to some yi here. So the x, which is the input, is becoming a y. So x is becoming a y by multiplying it with a w and adding a b, which is why we show it like this. F of xi semicolon w comma b. These are parameters. We say this, w is a parameter, b is a parameter. That has to be learned. And how do you learn it becomes the machine learning problem. And we have things like logistic regression and those methods which learn that. Now, a linear classifier with bias eliminated, we can also write the equation as simply y equal to wx transpose or w transpose x. It should have been wx transpose. Yeah, that's what it is, wx transpose. There's no b here. And so this says the way to get rid of this b is to treat this mathematics here, wxib, as simply w and b, where we simply add one more column here on this side, and in this xi we add one more element here, 1. So what we're doing is we augment the matrix. We say this is an augmented matrix by one more column here, and then the x is, I guess this is an augmented vector here. Actually, the term is for the vector and the matrix. So we say it's an augmented vector. One more element with value 1. In which case, we learn all of these elements. We need to learn all of these elements. And these elements can be learned using either pure linear algebra, no gradient descent or any of that kind of fancy stuff. And it's possible to get a linear algebra solution to the problem. Linear algebra solution means just multiply your matrices and so on. Yeah. Mihir, how much more time can you give me?
Probably more 10 minutes.
Oh, 10 minutes, okay. All right. All right, so let's look at this linear transformation AX equal to B, where A is, so we just saw this kind of an equation, W transpose X, right, of that kind of a thing. And we have A is n by n and B is in Rn. More explicitly, if we write like this, AX equal to B, this is a set of n equations in n unknowns. We can regard it like that. So it becomes simultaneous equations. Oh, wow. When we are multiplying an x, a vector x, the cat is your x, and we are multiplying the cat with a matrix, poor cat, and it becomes a set of values, b's. Okay, so this is we can say that n equations in n unknowns. This is what it would look like, simultaneous equations. So we can view A as a linear transformation of vector x to vector b. So this is the nature of a linear transformation. Sometimes we wish to solve for the unknowns x when A and B provide constraints. So we've got the situation. We can also formulate the problem. It's not exactly the same as what we had in the previous slide. We can formulate the problem like this also and say we need A and B are fixed, and then we need the values of x. So we can have that. So anyway, we'll see, we'll encounter that some other time. Identity inverse matrices. Matrix inversion is a powerful tool to analytically solve AX. So if you have a set of simultaneous equations, and we say, okay, I have a set of simultaneous equations for you here, and tell me what is the solution to the problem, which is what is the value of x for that. A consists of all the weights on the left-hand side of the equation. B is all the values on the right-hand side of the equations. And to give a solution to this in terms of inverse of a matrix, we need the idea of an identity matrix. And I already mentioned this earlier on. So an identity matrix looks like this. All the diagonal elements are ones and the rest of the elements are zero. We call it as I3. This is an identity matrix in 3 dimensions here. And identity matrix does not change the value of a vector when we multiply the vector by an identity matrix. It serves the purpose like a scalar value 1. This is a matrix version of it. So once we know what an identity matrix is, we can talk about a matrix inverse. Inverse of a square matrix A is defined as A inverse A equal to I. We can now solve AX equal to B as follows. AX equal to B, we can multiply left-hand side and right-hand side by A inverse. This is an inverse. Okay, A inverse has been defined here on the top right. And so we say A inverse A is just I, right? And then this is A inverse B. So in which case, when you multiply a vector by an I, it's just X. So this says, if you have a set of simultaneous equations, isn't that cool? You have a set of simultaneous equations in so many variables, and you want to know what is the answer to the this set of simultaneous equations. Don't bother doing cleverly multiplying things and eliminating variables and all that. It simply says, just express it as a matrix AX equal to B, and your solution is, as long as you know how to invert a matrix, then that's it. Actually, inverting a matrix in using all these NumPy and all these numerical tools, if you have a matrix and you say, go bring me the inverse, it just brings you the inverse. That's it. So it's a one-step solution to solve a set of simultaneous equations. But this depends on being able to find A inverse. If A inverse exists, there are several methods for finding it. How do you find A inverse? It turns out inverse doesn't always exist. Solving simultaneous equations. So AX equal to B, where A is m by 1 times m plus 1 times m plus 1. We just saw why we want to increase the size, the column vector by 1. So X is m plus 1 times 1, set of weights to be determined, and B is n times 1. Okay. So example of solving linear equations in linear regression. Where does it set of simultaneous equations, where is it useful in machine learning? In linear regression. In linear regression, we are saying we have a set of observed values, give me the answer is this value. Like a car that is an autonomous vehicle. You need to figure out the speed of the car, the accelerator. That is a scalar value, right? It's like, is it 10 miles per hour? Is it 20 miles per hour? Is it 30, 40, 50, whatever? You think of it as a continuous value. So that is what is appearing on the right-hand side. And we have a form where we have an equation of this form. T is the target value. And then this phi is called a design matrix, M by N design matrix. So we have M features for N samples. So we're saying somehow we've created a data set of, we have N samples. Each sample is corresponding to a particular frame we have seen before, and so that is expressed in the form of a vector, and we have features for every one of them, right? So for every one. So there are M rows corresponding to the samples and N columns corresponding to the dimensions in the observation. So it's an M by N. We call it as a design matrix. And we are saying we have a design for every one of these situations. There is a corresponding output. When we had that picture, what was the speed? When we had different picture, what was the speed? So this is a vector here. So we are saying if this is the case, let us figure out this W is a weight vector of M value. So we want to learn how much to weight each of these features to get that value. What is the importance of each feature? So that is a problem of linear regression. And we just said, if that is exactly the problem of linear regression, and we just saw in the previous slide that if you have a problem of the form AX equal to B, in this case it's phi W equal to T, and you're given me the data set which defines phis and the T's, you only need the W's. And we just saw in the previous slide, then the solution is just to take the inverse of this phi matrix and multiply by T. That's it, one step to learn linear regression. So it looks like that, you know, matrix inversion. So, and how do you find the matrix? There are two closed form solutions. One is matrix inversion X equal to A inverse B, and Gaussian elimination is another method. And so matrix formulation, we just saw this thing, the set of equations, and we can find the inverse of the matrix by just invoking inverse. And there are also, when you have a set of simultaneous equations, another solution to the problem is what's called Gaussian elimination followed by back substitution. If you have a set of simultaneous equations like this, x plus 3y minus 2z or 2z is equal to 5, like that, you express that as a matrix, and you can add and subtract the columns and play around it cleverly and bring it to this form, and you say, ah, there's your solution, minus 15a2. So this is called a closed form solution to the problem, either by Gaussian elimination or by matrix inversion. And you can solve important problems such as how to drive a car. Wow. Car driving is nothing but taking a bunch of snapshots and knowing the speed with each snapshot and putting it all in a matrix and just running it through a matrix inversion. So the whole problem gets solved in principle by a single step, because inverse is already available to you in TensorFlow and all that, right? But disadvantage of closed form solution, if A inverse X, the same A inverse can be used for any given B, but A inverse cannot be represented with sufficient precision. It is not used in practice because we're talking about huge matrices and, you know, number of samples, number of features, and so on. Number of features can be 1 million. Gaussian elimination also has disadvantages: numerical instability, division by a small number, order n cubed for an n by n matrix. If you have a 1000 by 1000 image, which leads to 1 million pixels, the complexity of solving the problem is a million times 1,000. How much is that? It's a billion operations to do to solve the problem of finding out the weights to multiply your input by. So software solutions use value of b in finding x, derivative between b and output. This is where the machine learning programs come into play, saying, while a mathematician would say that's all you need, matrix inversion, this is, oh, wait a minute, I'm a computer guy and I need a reasonable answer that I can implement on a computer. And this is going to require some cleverness, which is an iterative solution, right? Mihir?
Yes, Professor.
All right.
We can start with the quiz a little
Right.
bit early.
Okay.
Did we introduce Saugata to the class?
Oh, Saugata is here?
Yes.
Saugata, please wave to me on
Hey,
my.
Professor.
You are there? Okay. All right. Saugata is, I can't see you on my reduced screen here. No, anyway, I have to worry about this zoom ability here. Okay, hopefully you can all see Saugata. Saugata is going to be also helping run this course. He's a half-time TA for this course. He's also a half-time TA for the information retrieval course. So he's going to divide his time between these courses. And he'll be involved in helping us set up the projects and evaluate them and so on. While Mihir is the lead TA for this course, Saugata is going to be helping out, given the amount of work you're all going to be doing with all your homeworks and or projects and so on, right? So welcome, Saugata. Happy to have you. And we understand if you can't be here every class because they meet at the same time, right?
Yeah.
So, yeah, you can kind of divide your time, or if you find that this course you know less about and the other course you know more about, spend more time here. I'll leave it up to you, but Mihir will really appreciate your help. So that's Agata, and that's all. And so I barely finished half the slides on linear algebra. We are at slide 25. So I'll continue with linear algebra because along the way you discover that there are solutions to machine learning problems just using linear algebra, inverse and matrix and all this. So we need to know that before getting into fancier stuff. All right. Okay. So Mihir, you want to take over?
Okay, Professor. So the quiz one is live on UBlearns. So if you can open your UBlearns and go to CSC 4574 course, yeah, under the section of quizzes, you'll see that there's a quiz one item created for you. You simply have to log on to UBlearns and open up quiz one. All the questions will be displayed in just one screen. We'll have 15 minutes to solve 15 questions. Um, uh, we request that you all start at the exact time. So you can all start right now and you have 15 minutes to solve the 15 questions. So best of luck. And if you have any questions, you can ask here um, on Zoom. Let us know if you have any problems connecting on UBlearns.
They're trying to craft their message from our scientific organizations.
Of sedition on Facebook, stating without evidence the agency was harboring a resistance